So I want to start with this disclaimer or claimer, whatever. Robotics has been almost here for the last 70 years, right? There's lots of excitement around robotics, but it has always been coming. It's almost like fusion, but not 30 years away, but almost here, okay? So, and I want to start with a brief history of why it has been almost here for the 70 years and what has really changed since then. So if you look at this video or the result, this is a robot, and what this robot does is it sees this image and it arranges the object in front of it to match the image, okay? And it's completely autonomous. Now, if I colorize the video, made a nice generative AI filter, you cannot distinguish if this result is from today or is it from 60 years ago. So this was the first major result in robotics about in 1960s, okay? Now, if you see the current progress in robotics, a lot of work happening, a lot of papers, a lot of research. One thing you will notice a lot is this whole new wave of teleoperation, these leader-follower systems where you collect demos, right? Let's see this video. Any guesses for the year?
One exhibit at the Nuclear Congress in Philadelphia has the perfect formula for popular appeal. 2 amazing hands plus 1 pretty girl. The purpose of the display is to demonstrate the sensitive precision of the master-slave arm used to handle radioactive materials.
Look at the precision. Lighting a matchstick.
You can light a cigarette and keep right on working.
All right. Any guesses on the year? I think the sound here gives it away. Like it's not 2019 or something. But so I'll not take the guesses. 1957, 68 years ago. Like it was pre-computers. Okay. This one now everywhere you open LinkedIn, Twitter, everywhere things are going viral of robot parkour, this and that, whatnot. Look at this. Robot juggling balls, playing whatever, like what is this called? Hockey? I don't know this thing. The right one. This is from 30 years ago, right? And even when people say, okay, this is all good, but we don't have robots that can do pick and place. This is very cool work from Berkeley. Back when I was doing Ph.D. over there from Ken Goldberg's group, DexNet. This is 8 years ago. And this is not even the first version. Their second version could pick up almost everything in front of the robot. And if you are wondering, this is not your VLA or this billion parameter model. It's just a tiny model done by one PhD student over the course of his PhD, maybe in 6 months or something, okay? So what is the catch here? Like being the last talk of the day, so it's a bit demotivating to show you all this and say robots is almost here for 70 years. The catch is we see all this, but still no robots around us. So what has been missing? So what has been really missing is a general brain for robots. The hardware has been existing for years. There's 68 video before you had computers, you had these robotic systems lighting matchstick. So it is something to ponder about that how far have we come in the field. And this is basically what led this birth to what we call today Moravec's paradox. Hans Moravec, he was also professor at CMU back in the day. I don't know where he's right now. It's very hard to find. But this paradox is called hard problems are easy and easy problems are hard. So robotics is not an area that has now become hot after language or vision. AI was developed for robotics. If you read the initial Alan Turing's paper in 70s, this was actually about robotics. And these guys, Marvin Minsky, Hans Moravec, all these people worked for 20, 30 years because they thought robotics is the easiest problem. So they began with that. And after 30 years of hard work, they realized that what they thought was exactly the opposite. They thought playing backgammon, checkers, chess was hard. And pick and place, moving things, arranging is super easy. But in 30 years, they could solve every other problem but this. And hence, this paradox came into play, which what humans think is easy actually is hard, what humans think is hard actually is easy. And we are seeing this Moravec's paradox happen in front of our eyes in the last 3 years. Our notions of intelligence have completely changed in front of us. Right? This is a classic example given to us. Like this system could beat Gary Kasparov in like 90s, but still we don't have a robot that can reliably move stuff on a chessboard. Now, as soon as I say this, tomorrow somebody will make a demo, say that, oh, look, my robot can move chess like the queen from this position, this position. That's not what I mean. Like, you understand the robustness, the generalization. I can drive a car, you can drive a car, you can play chess, you can open door. Same brain everywhere, doing long-term reasoning, long horizon, short horizon, everything into one. And that's the definition of AGI we should be targeting for. Okay? So how do we go about this? Now, of course, we have not solved this problem. We are very, very far from solving this problem. If anybody says other way around, this, I completely disagree. And hopefully you will be too, like with the 70 years of literature behind us. So how do we go about this? So in this talk, I'll not give a solution, but maybe a direction as to how can we think about solving this problem in the next several years from here onwards. So I'm not saying AI has not made progress. There is immense progress around us. And the magic sauce we have seen behind this is the only, I would say the only recipe that has really worked in AI in the last 70 years is this. Build your large, diverse data set, train your big, large models, and make money, pretty much, right? This is the magic sauce of major AI successes. We see this behind LLMs, we see this behind generative models, vision models, etc. So the recipe here is scale, okay? A scale of data, being able to increase your data and drive your performance with that data, okay? So it's both. You cannot just throw data, you have to also improve performance with that increasing data. And that's the recipe behind all these AI progresses, okay? But unfortunately, for all of us working in robotics, this recipe is very far away. Why? Because there is no data for robotics. Now, here, not only there is no data, we are stuck with this real world earth or physics, which is very slow, so it's very hard to collect at that scale. Now here I want to really highlight what does scale mean here, right? Scale here is not 1,000 examples, 100 hours, 500 hours, million examples. It's not even billion examples. If you look at these GPT models, I think they don't even release these days how much data are they training on. But until 3.5, I think they released, it was 100 trillion plus tokens. 100 trillion. Now, the difference between 100 and our biggest data set in robotics today are million, roughly. The difference between 100 trillion and 1 million is 100 trillion. Right? So we have not really scaled robotics yet to really argue about this, okay, we are on the general path to solving robotics. So this is the problem we are tackling at Skild. We are going after building this, what we call this general robotics foundation model. Now this term is so common these days, it doesn't even, has lost its meaning completely. So just say a big model, okay? So we are trying to train a general model which can work across scenarios, across tasks, across hardware, okay? Again, I will say, across hardware, across tasks, across scenarios. It doesn't even make sense. It sounds completely absurd. Why or how will you make something across robot, across tasks, across scenarios? And in this talk, I'll give you some examples and hopefully make a case for this omni-bodied, omni-task general brain as to why that is very critical if we want to really solve AI or solve AI for robotics at least, okay? So any robot, any task, one brain. One of the major practical reasons for that is beggars can't be choosers. In robotics, we don't have data. So we cannot make a specification, oh, I'll only use data from my robot, this version, in this scenario, that scenario. We should be data hungry, and we are. So we should use any data source we can get our hands on. That's one of the easiest argument as to why you should have a general brain. You cannot afford to lose data just because it was on someone else's robot. It does not matter. You have to use every data, okay? Now, before I go into properties down this kind, if you train a general model, again, it's a big transformer and all those things, big data, SGD++, and all those tricks. But before I go into the, as to how do we train this, let me show you an example of what this can enable in the future if this kind of idea really takes off. So here is an example. In this video, we'll show a variety of robots, tasks, etc. And the underlying thing behind them is the general skilled brain across all of them. It's a very fast video, so we did not realize it while making it. So across different robot hardware, humanoid to quadruped, across different robotic arms, different tasks, whether it's mobility, like avoiding people, obstacle avoidance, or is it locomotion, controlling motors to move. These are the humanoids which are traversing the terrains of Western Pennsylvania. It's robust. Robustness comes as a property. It's not something you have to code in afterwards. Day and night, being messy. So here the demos are not very clean, look very lab-like, because they are, everybody is disturbing them. The scene is messy. That was about 2 feet high jump. Humans cannot sustain that. We have tried putting that pad and everybody fell when that guy hit them. Again, arm to hand, same model. This is, the trail goes on the road. This is going off trail. If you have lost AirPods, you would understand the pain of this task. Long-term navigation, short-term navigation, everything inside one brain. You kind of get emotional when you see you disturb, robot repeats, you disturb, robot repeats. Okay, so the question is going back, okay? The only point I have made so far is that if we want to build a general model for robotics, we have to get scale. Now, unfortunately, there is no scale for robotics until we actually deploy. So I call this chicken and egg problem of robotics. To train robots, we need data, right? But to get data, we need robots to be deployed in large numbers, like self-driving cars. But to deploy them, they need to work. But to make them work, we need data. So we are stuck in this loop in robotics. Now, self-driving car is one area, one very, very nice area, which got around this because cars were made first. Nobody still today buys car because they are self-driving. They buy car because they want to drive from point A to point B. And that helped us get data in return. But for general robotics, this is very hard. This causes this problem. So which means that if there is no data for robotics, how do we go about this? And this is where we have been working on for several years. Our company is 2-year-old, but we've been researching this area for like over a decade. We have to leverage alternate sources of data. And one such source, probably you already guessed by now, is human videos. Okay. Now, in my opinion, humans are also robots. We are just biological robots. Instead of motors and joints, we have muscles and neurons and all that. And the world is common. We want the robots to be operating in the same world where humans are, right? So we can really leverage how the tasks are supposed to be done. Whether you're a robot or you're a human, both the door will open the same way for you. So the door has to be moved from the corner towards the hinge in either direction. So the knowledge about the world is consistent whether a human does it or a robot does it. But there's a catch. Human videos, while they are scalable, because there are trillions of it already on the internet, so we can really go LLM scale, video scale in this direction. But the catch is with videos is they don't have forces. I cannot tell by watching how much force the robot is applying. In fact, I see this example always. If watching was enough, I would play like Federer, right? So you need to practice, you need to engage, learn about your own body. And that's where the second source comes into play, which is simulation. Okay? Both of these complement each other. One without other is not useful. Videos give you diversity, simulation gives you scale with actual physics and all those things. Okay? The combination of this can really unlock the recipe for training these big models for robotics. Okay? Now, simulation, and human video. So this is how we do it. But the general recipe we follow is as follows. We use this data at scale because you can generate trillions of examples through these data sources very quickly. So we use them for pre-training. Now, teleop, there is a good part about teleop. The teleop is it gives you high quality data. The data is high quality, but less in amount. Okay? High quality, less in amount. High quality, less in amount. What does it remind us of? This reminds us of the same recipe in LLMs. Use this data for actually post-training, which is what we do, in language, which we do in these general models. We use this high quality data for post-training, and for pre-training, we scale this with simulation. Now, this can be a recipe for the time being until we get robots work to a decent extent. Because if the robots get deployed in billions, then it's all self-sustaining cycle. You don't need any of this recipe. But you need this recipe to reach a point where robots are deployed in billions and millions. Okay? So this is how we build this general model, which is across robot, across task. We vary bodies of robots, simulation, etc. We can, so here is an example. So I'll show some examples. So this one here is trained only from videos, no sim data. So it can still do stuff by just copying how a human moves, but it has less. It's not that good at fine-grained motion because it has not yet seen simulation data and all those scenarios. But it can still follow human guidance to follow these tasks. To give you more examples, like this passed by earlier, we have a channel in our Slack called Right AirPod. #right AirPod, because everybody in our office just keep losing the right ones. I don't know what's about the right one. The left one they always have, they lose the right one. So we, inspired by this, we made we tried this task. Now this is an example of precise manipulation, right? Here you have to hold the AirPod in a certain way, turn it around, insert this. One of the main thing here is this is not real AirPod. These are cheap knockoffs from Temu. Right? Which means they're actually harder because they don't have that magnetic pull at the end, which you can softly just put and it just grabs by itself. You have to actually insert them and close them properly. And this is basically, we take our general model, and in this case, we fine-tune with about a few days of data, about a week or so, not 24/7, just 8 hours or 9 hours per day. And the model could just do it very reliably across all these examples. So this can unlock this quick transfer to new task in all these setups. Okay, you can also do more precise tasks. Now, when we thought it's very precise, but when we tried this, it worked almost very quickly, like just 1 day or 2 days of data. So it's actually not very precise task compared to the AirPod one, slightly harder. But you get the idea. When you build this general model, you do not think of tasks and skills as this major thing which you have to work on for years to develop. You can quickly adapt to them new tasks with a small amount of teleop data and other ways. One of the key highlight here, apart from scale and data sources, is the end-to-end part of it. This is very important because in all these results, what we are showing is that this model is operating directly from sensor input, the camera, and directly outputting command for the motors at high frequency. Okay, so model directly takes camera input, sensor input, directly commands motors at 100 hertz, which means there is no stack in between. We don't have this whole stack of mapping, planning, etc. It's all done in the model at multiple scale. Now, being a professor in robotics, probably it's hard for you to understand what does it mean for robotics. Robotics has been around mapping, planning, and everything for the last 70 years. And in this case, we are going completely end-to-end, even for things like navigation, as I showed earlier. Now, what this does enable, like you may have seen a lot of humanoid videos around the world. But if you try to think, you will not find that many humanoid videos, despite they can do parkour, jump, get up. But you will not find that many humanoid videos doing stairs. Just think carefully. Have you seen a humanoid video doing long stairs? Probably the only company that will come to mind is Boston Dynamics. They had shown some earlier ones with their old Atlas, but that was inside the lab. And their process was they would map every stair, the height, width. They have a full video on the YouTube explaining their procedure. So it's mapping and planning based. But otherwise, you will not see humanoid videos doing stairs. And you might see here and there, but those are easy stairs, which you can also do blind, like very big flat area, then a small height, big flat area, like these park stairs. They are much easier. But the harder ones are these stairs in your fire escape. It's kind of ironical that fire escape is supposed to be the stair which you go to if something is wrong in the building, and they are the hardest. So here what we do is we take our robot. This is operating from vision. Just to be clear, the reason you have not seen that because most humanoid results are blind. Blind as in the model is not aware of the vision input. It's processed separately, and that causes precision errors in these tasks. But here, this robot is operating completely end-to-end from vision. So if you notice, when it comes near the gap, it takes a small step, it stops, then takes a step after that. The model here is intentionally taking footsteps to go over things. It's operating from vision at high frequency. Now, vision versus blind, it's not just a difference of sensors. It's a major difference because the dimensionality of vision is very high. Like even a smallest image is like 100,000 dimensions, while body is like only 10 dimensions or 20 dimensions. So it can go over all of these things pretty smoothly. So this is what I mean by one of the newest building in Pittsburgh, and these are the fire escape stairs. I don't know how people will escape in this. Now this can go over a variety of scenes, scenarios. It's robust. Now many people ask how the robot is looking at the stairs. The camera is at the torso, so the camera is in this area, just so that it's not clear. So it can go over this. I think our idea was don't disturb the robot because we wanted one clean shot, but people can't help. That guy stopped in the background just to see the robot. You are disturbed. Look at this one. Pulling the robot from the neck on stairs. This is superhuman. Like we have tried this. If you are climbing stair, if you have force here, it's very hard to balance in this kind of lateral way. And again, what I meant initially, like humanoid, and this is human-sized humanoid. It's like almost 6 feet. Any small misplacement, any small error in mapping, planning can completely throw off the robot. But here we are not doing mapping, we are not doing planning. It's all operating from just the camera. The robot knows about its inaccuracies as it goes over this thing. So we had to really search for a scenario where there are so many stairs and outdoor area, nice looking, to really make the point. Now the benefit of having general brain is that we don't have to always do just useful tasks. We can also do fun, useless stuff, which is not very useful in terms of like actual deployment or stuff. But here, this robot is doing, vaulting. I just play it again. It's supernatural motions. And the interesting part here is it can engage with the world to go around it. It's very fluid. Like if you wrap it up in a cloth, etc., and mute the sound, it's very hard to know it's actually a robot doing this fluid motion, right? Now going further, the argument of omni-bodied brain is not only for generalization, data. There are other reasons also. Most people here are companies who are deploying robots and deploying models on robots. There is a big difference between a demo and the real deployment. In real deployments, the robots can actually break. Things can break, motors may go wrong, and that's one of the, now cars have had 100 years to improve the hardware. Like in self-driving, the car hardware has been improved over 100 years. But for robotics, we haven't had 100 years because we had not had usage for robots yet. So the robots can break, things can go wrong, and omni-bodied aspect also helps in that scenario. So here, for the comparison's sake, what we do is we train these specialist policies for these robots, and here we tied the legs. It struggles. Now, it's actually a good model. It works very fine. But when we tied the legs, or let's say a leg breaks here, we disable the motor by software. We lock one knee, and the robot completely goes haywire. So this is where, again, the omni-bodied part comes into play. But so far, I did not mention how is this omni-bodied thing working. The way it's working is by adapting in real time to changing situations. Okay? This kind of adaptation is extremely long term. It's sort of the emergence of the era of in-context learning for robotics. Now, in-context learning, I would say, one of the biggest insight in LLMs, before LLMs and after LLMs in language processing. But in robotics, everything, there is no such thing as in-context learning. We have to pre-train, we train a specialized system, and then we deploy them. So in this case, we are doing multi-episodic learning in context at test time. Robot sees its behaviors and adapts in real time. To show you an example, in the remaining few results, we will exclude all the robots from the training set. Okay? Just remember this. Whatever robots you will see now, they are not in the training set. So not only we will change the body, that robot is itself not seen. And it's completely zero shot. Now, if I ask you a question, if I start the robot like this, in this pose, and then I turn on the brain, and it's zero shot, how does the model even know, is it a dog? Right? Because humans were also quadrupeds. If you go far back into the timeline, we have same structure, there is no way to know if I start the brain in the body immediately, am I a humanoid, am I a robot? In this case, unfortunately, since we start like this and the IMU says I'm upright, the model starts to think it's a humanoid. So, but the thing is, it's a humanoid, and the model has never seen the robot also. This robot is never seen. The robot is not seen, the configuration is not seen. What happens? It tries to do it, it fails. But it's adapting live. So adapting, second trial, walks few steps, adapting. It's in context adaptation. In third trial, actually starts to walk. It's a real learning example. But this poor guy has no idea I'm a quadruped. I can just relax. So it's stuck in this uncanny valley here. Here, we take this robot, we tie the legs. Again, the robot is not seen during training. This is not seen during training. It's just completely zero shot. So we tie it. It's adapting live, adapting, struggling, adapting, doesn't just flip over, adapting, in context learning right now, adapting still. Okay, come on. Okay, learn to walk, right? So this is one of the major benefit of this. So here, you can also go do crazy things. You can change the body completely. This robot, it can easily work, but then you add these stills. Here, basically, when ChatGPT came out, people tried different things. Here, we are just trying random scenarios. Somebody asked today, did you try hopping on one leg? We said, oh, well, let's try this. So it's adapting, that can adapt. Kind of impressive. This is not even, you cannot even detect these stills as the thing. So it's all, it can adapt by feedback in real time. Just to show you now, before I show, so this is the power of the omni-bodied brain. I'm almost on, my time is up. So I'll show this one last video, but before I show that, I apologize. And you will know why I say that. This guy is stuck in the uncanny valley still. You can add weights to it. It has no idea it can relax and go down because not fine-tuned. You can jam the wheels. The robot was going on wheel. As soon as you jam them, it starts walking. What about 2 legs? It's kind of weird. Never trained before, never seen before. Also for manipulation, different DOFs of the arm, different robots. All right, thank you.